Hello, 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 and welcome back to Shiksha DaCosta. Today we are going to review the unit Solving Problems Involving Quadratic Relations. If you're done this unit, hopefully by now you have learned how to solve quadratic equations and how to interpret their solutions with respect to those relations. Hopefully you're also able to use that idea to solve problems that involve quadratic relations. And here is a list of success criteria that you might have. So do you think you're able to expand and simplify second degree polynomials, in other words, quadratics, using different tools and strategies? Can you take a polynomial expression and factor it using things like common factors or difference of squares, using all sorts of different tools and strategies to do that? Can you determine, or did you determine, through an investigation, what is the connection between the factors and the x-intercepts of a quadratic in factored form? Are you able to interpret a real and a non-real root of a quadratic equation using by investigating that through graphing technology? Are you able to take a quadratic that's in standard form and express it in vertex form by completing the square? Are you able to sketch or graph a quadratic that's in standard form? Have you explored the algebraic development of the quadratic formula, and can you use it and all of these other strategies to solve quadratic equations? Have you figured out what is the connection between the zeros and maximum or minimum of a quadratic, and can you find those from a graph of a parabola or from the equation of a quadratic relation? And finally, can you use all of these skills all put together to solve problems that come from a realistic situation? If that situation is represented to you by a graph or an equation, or can you even come up with that equation yourself? If you can do all of these things, then you have successfully completed this unit. You know how to solve problems that involve quadratic relations. But let's go through all of these one at a time just to make sure that you've got a handle on all of it. In this unit, we learned that many problems in life can be modeled using quadratics, but once that algebraic expression is created, it can look pretty complicated. And we can simplify that, and quadratic relations, to simplify that, it's usually the case that we have to multiply two binomials. Now, generally, simplifying involves expanding all the brackets and collecting like terms, and then rearranging those terms from the highest exponent to the lowest. If you're multiplying binomials, two algebraic expressions, in a binomial would have two terms each. But even if it's not a binomial, even if you're multiplying any two algebraic expressions, you just multiply each term in the first one by each term in the second. Now, if you have a binomial, right, that's just two terms in each, there's an easy way to do this or to remember to apply this rule, and that hint is the word FOIL. FOIL stands for F stands for first two terms, O stands for outer two terms, I stands for the inner two terms, and L stands for the last two terms. So just again, going back to this expression right here, you multiply each term in the first expression by each term in the second. So A gets multiplied by both of these, and then B gets multiplied by both of these as well. And then finally, you just add all of those together. If you'd like to go backwards, if you'd like to do the opposite of expanding and simplifying, you can factor something. And the first and easiest step to factoring an expression is to look for all of the terms. What is a factor that all of them have in common, and what's the greatest of all of these factors? You can just divide all of the terms by that greatest common factor to create two separate factors. And that common factor doesn't actually have to be a monomial. We looked at in this unit that it can even be an algebraic expression. If you have a quadratic in the form x squared plus bx plus c, in other words, there's no coefficient of x squared, if that can be factored, you can use something called the sum product rule to factor it. You're just looking for two numbers, which I'm going to label r and s, that when you add them together, you get b, and when you multiply them, you get c. And this quadratic would, or this algebraic expression would then just be factored into x plus r and x plus s, those two numbers right here. Now, if there is a greatest common factor, definitely factor that out first, and that will help reduce the expression maybe into something that looks like this. If the sum product rule fails you, you might want to look at whether or not the expression is a special case of quadratics. So if it looks like a squared minus b squared, well, that always factors into a plus b and a minus b. If it looks like a squared plus or minus 2ab plus b squared, so in other words, the first and the last terms are square numbers, and the middle term is 2 times the square root of this times the square root of this, well, then you have a perfect square trinomial, and it can be factored into a plus or minus b squared, where this sign is the same as this one. If that fails, well, you can always use decomposition to factor a trinomial if it is factorable. So if the coefficient of x squared is not 1, if there actually is a number there and it's not a perfect square trinomial, to use decomposition, you just multiply a times c. Then you take the two factors of that. You have to find two factors that do add up to b. And you're going to split this bx term into two separate factors, which we're going to name, Rx and Sx, where R and S are those two factors that multiply to AC and add to B. When you split that Bx term up into two separate factors, you're going to group them and factor the first two and the last two by using greatest common factoring. And if you do that correctly, you should end up with two brackets that have the same exact expression in them. The coefficient of those brackets is your first factor, and the expression in the bracket itself is another factor. The reason we actually learn how to factor is that helps us go from a quadratic that's in standard form to factored form. And this is the expression of a quadratic in factored form. The reason this is so useful is we can very easily identify the zeros. Another word for zeros might be the x-intercepts or the roots. We can easily identify them when it's in factored form because it's any value of x that makes either of these two factors equal 0. In this case, the zeros would be r and s, because r minus r is 0 and s minus s is 0. You can also create a quadratic relation in factored form if you know the zeros and you know one other point. So if you know r and s, you could just start with this expression, replace r and s with those two zeros, and replace x and y with that one other point's coordinates. So just substitute those in and then just isolate a, and there you have all the three parameters you need, a, r, and s. Then we looked at completing the square. Completing the square is a process that takes us from standard form to vertex form. If we were in vertex form and we wanted to go to standard form, we could always use FOIL and expand this and then collect your like terms, et cetera, et cetera. But to go backwards, this is the process, completing the square. Completing the square is quite a complicated and lengthy process. It's one of the few ones that always annoys me when I have to do it. But of course, I'm going to walk you through all of the steps involved in doing that with an example. To complete the square, the first thing you do is factor the a value out of the first two terms. Just like that. So I factored 3 out of these two. Then you take the b value, the coefficient of the second term in the brackets, you divide it by 2, and then square it. And that number right here, you add and you subtract it inside the brackets. And by doing that, we haven't changed the right side at all. We've just basically added 0. Now, this right here is a perfect square trinomial, but this -9 kind of messes us up. So we're going to get that out of the brackets, the negative version of it, by multiplying it by the coefficient a. So we know that that's going to give us -27 in this case. And now we have a perfect square trinomial, which we can very easily factor. And it's always going to factor to x plus half of this number. So half of 6, of course, is 3. X plus 3 squared will be this result. And then I can also at the same time combine these two like terms on the outside. And just like that, we end up with a quadratic in vertex form. Now, all three forms of a quadratic give you information about one point on the graph. Standard form tells us the y-intercept. From standard form, we can we can complete the square to turn it into vertex form like we just saw, and that gives us the vertex. If we want to go back, we can always expand and simplify, and we can then take standard form and factor it to get factored form. And factored form, of course, tells us the two zeros or x-intercepts or roots. And if we wanted to go back to standard form, if we had factored form, very simply, all we have to do is expand and simplify. So to turn to standard form, expanding and simplifying is always the method. Factoring and completing the square are much more involved and require many more steps, but that's how we would go from standard to vertex or standard to factored. Not every quadratic has a factored form because not every quadratic goes through the x-axis. Not every one has a y value of 0 at all. But if it does, you can use these techniques to find 4 different points. And the more points you have, the easier it is to sketch that smooth parabolic curve. And as I mentioned again, not every quadratic has real 0, so this is not always possible. Now that we know how to go between those, we can solve quadratic equations. Unlike linear equations, we can't just isolate x, right? We'll always end up with an x squared or an x term on one or the other side. Instead, we have to make one side of the equation equal 0, and then if it's factorable, just factor it. And then set those linear factors equal to 0 and solve it to find out the values of x that make that true. But if it's not factorable, one thing you can do is complete the square to turn it into vertex form, and then you can actually start to isolate x like we would with a linear equation. Now, that might be both of these might be quite involved, and in fact, not every quadratic is even factorable. So one thing that will work in every case is to use the quadratic formula. If it's in standard form and every quadratic has a standard form, you can just plug those a, b, and c values into the quadratic formula to find the roots or to find the zeros. We also explored when we learned about how to solve quadratic equations that the vertex is at these coordinates always, and we can get that right from standard form as well. The equation of the axis of symmetry is always x equals the x coordinate of the vertex, so that's another thing we can pull right out of standard form. Finally, we looked at real-world issues. You can always use the graph of a quadratic to come up with its equation, and its equation is super useful to solve problems really accurately. You can always turn that equation into factored or vertex form by factoring it or completing the square. Or if you have it in factored or vertex form, because that's how you obtain the equation in the first place from the graph, you can always turn that into standard form. And to do that, all you have to do is expand and simplify. Once you have it in standard form, like I mentioned, you can find the zeros using the quadratic formula. You can find the vertex using that formula. You can also ascertain that this would give you the maximum or minimum, the y coordinate of the vertex. But whenever you're dealing with a real-world problem, as soon as you start to introduce a variable like x or t or whatever have you, you should always define it. What quantity is that variable actually measuring, including what unit are you using to measure that? You should also, when you're done solving, include a final statement that summarizes your findings. And when you write that, you might find that one of your solutions doesn't actually make sense. And so if that's the case, you may say this solution is not allowed or inadmissible. And if you're doing that, you do have to say why that solution doesn't make sense given the context of the problem. And that's it for this unit. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.